Welcome to Physics 1. Today my background is the galaxy NGC 7331. This is discovered by William Herschel in 1784. And that's actually pretty impressive because finding a galaxy with a telescope is difficult. Maybe it was easier back then because there was less light pollution, but it's not easy to find galaxies. So the fact that he was able to do that in the 1700s was very impressive. This galaxy is 50 million light years away in the Pegasus constellation. So galaxies are not really visible by the naked eye except for the galaxy Andromeda, which is our nearest neighbor. You could sometimes see that, but you really need at least binoculars or a telescope. And most of the time it's blocked out by light pollution from the cities. So if you have binoculars and you're in a dark place, you could actually see the galaxy Andromeda. It's not going to look probably like this. This was taken with the Hubble Space Telescope, which has unbelievable resolution. Since the Hubble Space Telescope is outside of the Earth's atmosphere, it's able to take much better pictures. The atmosphere actually causes a lot of interference and prevents focusing, which is why it's not really possible to get pictures like this from an Earth-based telescope. So when the Hubble Space Telescope came online and started taking pictures like this, it was revolutionary. If you want to see more pictures, go to hubblesite.org, and they have the most incredible pictures of our universe out there that are imaginable. I have a collection of Hubble images, and I always look for new Hubble images. This is the latest one that I found. But go to Hubble site on Google, and it will you'll see the most amazing pictures of our universe. And what's really interesting is that this was 50 million light years away. So when you look at this galaxy, you're actually looking backwards in time. You're seeing the light that left 50 million years ago. That's how long it took to travel to Earth. Now, other galaxies are so far away, it's almost unimaginable. And when I say 50 million light years, 1 light year is the distance it would take for a beam of light or a photon to travel in 1 year. Now, a photon or light travels at 3 times 10 to the 8 meters per second. How far is 1 light year? 1 light year is 9.46 times 10 to the 12 kilometers away. It's almost an unimaginable distance. And for 50 million years, it was traveling that far for every year and to get to Earth. So it's really a long ways away. Well, let's get to the lecture. This video is intended to go over some of the bigger concepts in chapter 10, which is all about energy, kinetic energy, and potential. So we're also going to be discussing something called work, which is the amount of energy used when a force is applied over a distance. So work is equal to force times distance. So for example, if a blue whale was swimming in the ocean and the force of drag was acting on the blue whale, as it was swimming, it would be using energy to overcome the force of drag. The force of drag would be doing work against the whale and slowing it down. So the whale, in order to keep swimming at a constant velocity, is going to have to use energy to keep moving forward. If it didn't, then the whale would come to a stop. Now, whales are incredibly aerodynamic, and so if a whale was swimming at 20 miles per hour, or about 6.5 meters per second, it would take several kilometers before the force of drag started to slow it down. And in that time, the force of drag would change um, from a high Reynolds number to a low Reynolds number, depending on when its velocity got low enough. So as it slowed down, the force of drag decreases, and so it would be able to travel even farther. So they could coast for several, maybe 5 or 6 kilometers. Now, blue whales are always usually swimming, and the thrust from their tail is equivalent to 60 kilonewtons. So as they're swimming, they have a huge amount of force. This allows the whale to dive underwater, which is one of the things that we're going to look at. We're going to look at all of the forces acting on a blue whale, which includes the force of thrust from its huge tail fluke, which is 60 kilonewtons. Then the buoyant force, which is a force that causes things to float. So the buoyant force acts on an object underwater because it's displacing water. As an object pushes the water out of the way, all of the water on top of it pushes back down and tries to push it up. The water wants to return to its original position. Because you've displaced a certain amount of water, that creates a force. So you've got the buoyant force. You've also got gravity pulling the whale down, which is a massive force on a whale because whales weigh about 100 tons, which is a huge mass, the biggest animal that's ever lived. And you've also got the force of lift. As the whale is going through the water, it's got huge flippers, and those flippers enable the whale to steer through the water, basically. Let's talk about Chapter 10, Energy and Work. The chapter goal is to introduce the concept of energy and to learn new problem-solving strategies based on conservation of energy. And that really, I think, is one of the main points of this class, is to learn problem-solving strategies. So once you do these problems, the ultimate goal would be able to take what you learn and apply it to other problems. All right. Dolphins and whales have kinetic energy. So as they're swimming through the water, their movement can be characterized by kinetic energy. So kinetic energy is equal to 1/2 mv squared. So the faster the whale or the dolphin is swimming, the more kinetic energy it has. When it jumps out of the water, it also has potential energy. So when it gets to the top of its jump, it has a lot of potential energy. When it gets to the top, all of its kinetic energy is converted into potential energy. So there's an interplay there between potential and kinetic energy, but we'll get more into that later. And of course, thermal energy. When you are moving, you can create thermal energy either through friction or a human. When you exercise, you create thermal energy that your body gives off in the form of heat. All right. In this example, a woman is transferring energy into the system. She's using a jack to increase the height of the car. It takes her energy to do that. As she moves that handle, she's putting energy into the system, which raises the car up. So she's doing work on the system to get it to a higher level. When she gets to a higher level, if the car were to fall, that energy that's stored there could become kinetic energy and it could start to fall. Let's take this book by Edward Abbey, The Monkey Wrench Gang, and let's drop it. So as I raise it up, I'm doing work to lift this book up. It takes energy for me to raise it. As I let it go, that energy becomes kinetic energy. So we went from putting potential energy into the system, then we let it go and it became kinetic energy. Now, where did that energy come from to move the book up? The energy was chemical energy that I stored when I ate my toast this morning. So my body turned my toast into energy that I can use to move things. So humans store all their energy in chemical energy, just like blue whales. Blue whales eat krill. They convert that into energy so that they can swim. So this woman, she's converting chemical energy into potential energy of the car, which can become kinetic energy. You can store energy in many different forms. Gasoline is a form of chemical energy in your car, and you can convert that chemical energy into mechanical energy. When you burn the gasoline, then you can make kinetic energy. You can cause the car to move by turning on the motor, and you will convert some of the energy stored in that gasoline into useful mechanical energy. The car starts to move. However, a lot of that energy is lost due to thermal energy. Okay, so the chemical energy in your tank of gas, some of it goes into doing useful work, but some of it's lost into creating heat. Humans are the same way. When you exercise, it takes a lot of energy to move, but your body also creates a lot of thermal energy. So all of the energy can be accounted for. It cannot be destroyed. It has to be conserved. So whatever energy you start with has to go into some other form. So you could change potential energy into kinetic energy and thermal energy. Another example would be a hydroelectric dam. As we store up water behind the hydroelectric dam, the water flows down through a turbine. It spins a turbine and it creates electricity. That electricity then can go to power things in your appliances and do useful work for us. But we get that energy by putting water behind a hydroelectric dam. As the water falls down due to gravity, then it can create electricity. But gravity is the thing that's doing work. So as the force of gravity acts on that water and pulls it down, that work can get converted into electricity by a turbine. So, all right. As they slide, so here's some happy people on the slide. Water slides aren't open right now, but if they were, as they go to the top, all of their energy is in the form of potential energy. As they fall down, it gets converted into kinetic energy, and they start going faster and faster. If we know the potential energy at the top, we can figure out what their final velocity is at the bottom. If all of that potential energy is converted into kinetic energy, then we can calculate what their velocity is going to be at the bottom. All right. So looking back at with motion with constant acceleration, in chapter 2, we learned how to describe the motion of a particle that has a constant acceleration. And we'll use this constant acceleration equation to connect work and energy. Okay, so this equation right here is actually pretty useful because this is sort of a precursor to kinetic energy. We've got the force, an acceleration due to something like gravity, and our distance here, spoiler alert, if we multiply by m, then this becomes kinetic energy. This is also kinetic energy. We've got a potential energy right there. There it is. So we're going to multiply that by m. That's going to turn this into an equation that tells us about energy. So if we multiply both sides by m, then we get a potential term, and we get our kinetic. So let's actually go ahead and do that. Okay, so let's start over here with our kinematic equation, where Vx f squared, our final velocity squared, equals our initial velocity squared plus 2ax times delta x. So we've used this equation a lot before, and now we're going to basically change this into my expression for energy. So what I'm going to do is I'm going to multiply both sides by the mass of an object. So multiply both sides, we'll get m times vx of f squared. And I'm going to bring this one over here, my initial velocity, minus mvi squared, which will equal 2ax times delta x times m. Don't forget the m. Now I'm going to divide both sides by 2. I'll divide by 2 here, divide by 2 here, divide by 2 here. Well, now we come to a place where we can define a term called kinetic energy. So we'll say kinetic energy is equal to 1/2 mv squared. This is equal to energy. It's got units of energy, which are kilograms times meters per second squared. That's going to be have units of joules. Okay, and over here, now we've got this interesting term here. This is a times m times delta x. Now this is really interesting, and let's go down here and write this again. Okay, so we're going to have 1/2 m times vxf squared minus 1/2 m vxi squared, which is going to equal mass times acceleration times delta x. Now, we know that mass times acceleration is equal to force, so we're going to write this as force here. So we'll say the force times delta x is going to give us, this is going to give us work, because if this side is equal, has units of energy, once we multiply by mass, then this side also has to have units of energy. Now here we've got our, this is our change in velocity. We've got our final and initial. So we could really say this, we'll call, what we can do is we'll say that this whole thing is equal to our change in kinetic energy. So delta KE is equal to a force times a distance. And now F delta X, this is something very special, and this is called work. So we're going to say that we're going to define this quantity called work. And so we'll say our work is equal to F times delta X. And this has units of joules, and 1 joule has units of kilograms times meters per second squared, because we've got mass here, then we've got meters per second squared. So this is meters squared per second squared. So yes, meters squared per second squared, because I looked at my units and that's what I. Now, we could define this another way. We could define this as a Newton meter, because 1 Newton has the units of kilograms times meters per second squared. So now this becomes Newton meters, and that is going to equal a joule. So this is work is has the units of joules. And what this is telling us is that force applied over a distance is the amount of work that we're going to do. So for example, if let's say a whale gliding through the water has a certain kinetic energy, and the force of drag acts on that, acts on the whale. Over time, the force of drag is going to take away energy from the whale, which is going to do negative work on the whale. So its kinetic energy is going to decrease as the force of drag is acting on the whale. I like to think of it as drag is taking energy away from the whale. So it's doing work against the whale while it's swimming. And this corresponds to a change in kinetic energy. So delta KE is equal to 1/2 mv x final squared minus 1/2 mvx initial squared. Okay, so put a box around there. So this is our change in kinetic energy. So the change in kinetic energy corresponds to an amount of work. So another way you could think of it is that the kinetic energy of an object will not change unless there's a force acting on it. So if a particle has a certain velocity, then it has a certain amount of momentum, and it has a certain amount of kinetic energy. And that's not going to change unless a force is applied over some distance. So as the force is being applied, the force is going to do work on an object, and that's going to um, uh, that's going to change the kinetic energy. So let's look at a force that we could use for this example. One of the most obvious forces that you encounter every day is the force of gravity. So we know that F equals m times g. Okay, so if the force of gravity is acting on an object over a distance, so we'll say gravity is going to do work on an object. So maybe this is a blue whale. Let's say, just for the sake of argument here, we're going to do this on a blue whale. Okay, so let's just do a thought experiment here. And we haven't gotten to buoyant force or anything like that, but we can think about what happens to a blue whale as it starts to dive. Okay, so a blue whale typically goes down to about 300 feet, let's say. Okay, so 300 feet, and this will be about, we'll say it's about 100 meters. Okay, that's reasonable. So the whale goes down here, and we don't know what angle it's going down, but we know that the whale is going to change in height by 100 meters. Okay, so our distance here is going to equal delta x. Okay, so as the force of gravity is acting on our blue whale here, it's falling down here because blue whales can dive down, and so gravity will be pulling the massive blue whale down to the bottom of the ocean. Now, uh, you have to remember that there are other forces that do act on the whale, and let's not forget the tubercles on the whale's flipper. If you ever wondered why blue whales have bumpy flippers, those little bumps have a name. They're called tubercles. They actually help the whale swim more effectively because the whale can steer better with tubercles because the water is channeled along the whale flippers. Okay, so let's say our giant blue whale, 100 tons, is going down 300 feet. Now, when blue whales are in trouble, they can also sink to a depth of, say, 1,600 feet, right? Or we'll say about 500 meters. That's reasonable, okay? So when they get in trouble, they can go even deeper. All right, let's see what happens when our whale dives down. So the forces of gravity is acting on our whale here when it's going to dive down and either get some prey or maybe it's escaping from some type of predator, although blue whales don't really have any predators except humans. And fortunately, in most places, whaling has been outlawed. Okay, so let's say our whale is diving down here. We'll do 100 meters when it's feeding. Okay, so over the course of our distance, the work that's going to be done by gravity is going to be mg times delta x here. Okay, So this is going to give us something in terms of energy. And let's do our calculation. Let's say the mass of the blue whale is m equals 1.81 times 10 to the 5 kilograms. That is truly massive. G, of course, equals 9.8 meters per second squared. And our distance, delta x, we'll say is 100 meters. Okay, so 100 meters. Now we can compute the work that the whale does when it goes down to that depth, okay? And we're fighting against the force of gravity here. So gravity is going straight down. That's going to be m times g. So it only matters the distance that we move in the direction of that force. So the only thing that matters is the change in elevation of our whale. So as we go down 100 meters, that's going to be our change in energy. So if we put all those things together, then we'll have the work is equal to 1.81 times 10 to the 5 kilograms times 9.8, or 10 meters per second squared, times 100 meters. Okay, so this will in effect, and we made an approximation there that gravity is 10 meters per second squared. So this is going to be 1,000 times 10 to the 5. So that will increase this to 10 to the 9th. So our answer is going to be 1.81 times 10 to the 9th joules. Okay, so now let's imagine that the change in our kinetic energy of our whale, we can say, well, if the whale initially had a velocity of 20 or 9 meters per second, what's going to be its final velocity? So if the velocity was 20 miles per hour, that translates to 8.94 meters per second. Okay, so that's our initial kinetic energy. And now we're going to assume that if the whale has that initial kinetic energy, then as it goes down, it's going to correspond to an increase in kinetic energy. So our kinetic energy is going to change, and we're going to assume that the whale can steer, and so it will go down this distance, okay? And so let's put that in there. That'll be our initial kinetic energy. So we want to find the final kinetic energy. This is our initial velocity. We're going to find our final velocity using kinetic energy, and our expression up here, change in kinetic energy is equal to W. So maybe we need to write that down here for emphasis, okay? So the work that the force of gravity is going to do is equal to our change in kinetic energy. Okay, so the work that we did up here is due to gravity, and this is potential energy. We can call this, it's usually referred to as potential energy. All right, so in general, we'll say that U equals mg times h. In this case, h was delta x, our change in elevation of the whale. Now this is ignoring drag, this is ignoring the buoyant force and all the other forces, but we're just going to see what would the change in kinetic energy be, and thus what would our final velocity for the whale be if we only took into account the change in potential energy. Okay, so let's do the math. Let's put in our numbers here. Okay, so we are going to have mg times delta x, which is going to equal 1/2 mvx final squared plus 1/2 mvx initial squared. Now, I put it in this form because if you notice here, if we're just looking at our velocity, then our mass is actually just going to cancel here. So even though we got a number up here, we probably don't actually, we want to keep it in symbolic form over here. And then we can find out our final velocity, and our masses are just going to go away. We could keep it in terms of energy, and we can find the kinetic energy of our whale. So if we know the mass of our whale, which is right here, let's figure out what its kinetic energy is going at 20 meters per second. All right, so its kinetic energy is 1/2 mvx initial. We can take off the x there because it doesn't really matter. So v initial squared, right? And that's going to be 1/2 times 1.81 times 10 to the 5 kilograms. And our velocity is going to be 8.94 meters per second squared. Let's put that into Mathematica and see what we get. So we have 1/2 times mass of our whale, 1.81 times 10 to the 5th kilograms, then times our velocity, which is 8.94 squared. This is meters per second. Oh, hit the wrong button. Meters per second squared. All right, what are we gonna get? We are going to get 4.72 joules. All right, that's going to be our kinetic energy. So the answer that we get, its kinetic energy, is going to equal 4.72 times 10 to the 6 joules. Okay, that's what we get. That's its kinetic energy. So now we could find its final kinetic energy. So if we're going to do this just in terms of energy, we computed its initial kinetic energy here, and we're going to use this to find its final kinetic energy and hence its final velocity. Okay. All right, here's what we have so far. We found that the work done by gravity for it to descend 100 meters or 300 feet is 1.81 times 10 to the 9th joules. Its initial kinetic energy is 4.72 times 10 to the 6th joules if it initially has a velocity of 20 miles per hour. So now we want to compute its final kinetic energy and ultimately its final velocity. So how can we do that? Well, as we saw before, the work done is equal to my change in kinetic energy. All right, so that means work is equal to my final kinetic energy minus my initial kinetic energy. So I'm going to rearrange this and solve for my final kinetic energy. So I'll put final kinetic energy on this side. Work will go to this side, and I'll say plus my initial kinetic energy. So this is the sum of all of the blue whale's energy. And that is, it's going to have its initial kinetic energy plus the work done by gravity. Now, blue whales weigh quite a bit. So let's see what its velocity would be if we ignore drag, if we ignore lift, and all those other things just from a conservation of energy perspective. Because if this equation is true, it seems like our whale is going to be going pretty fast. But let's plug in the numbers and see what we get. So we will have 1.81 times 10 to the 9th joules plus 4.72 times 10 to the 6th joules. Okay, so let's put this all in the same units. So we'll say 1.81 times 10 to the 9th joules plus 0.00472 times 10 to the 10 to the 9th joule. So I converted this number here. I'm going to add it to this one. And so we'll get 1.81 times, and these numbers are all way over here. It's supposed to be 472 times 10 to the 9th joules. So when the blue whale dives, its initial kinetic energy is going to be pretty minuscule. Now, this means that when it's underwater, it's probably going to be going pretty fast. Let's see what velocity we get with this, because I'm pretty curious now. So this is our final kinetic energy, but let's convert that. Let's figure out what our velocity is going to be for this thing, because it seems like it's going to be pretty high. So our final kinetic energy is going to equal 1/2 mv final squared times 1.81, and this really didn't actually change our number that much. It did over here, but really its initial kinetic energy was not very high. But I'm going to keep those in there just because I like to wait until the end of the problem before I do significant digits, because if you get rid of them too soon, it can lead to errors. So keep those in until your final answer. Then you can put in the correct correct significant digits. So I'm going to solve for my final velocity here. All right, so that means I'm going to multiply this by 2 times 1.81 472 times 10 to the 9th joules divided by the mass of my whale. The mass of my whale was 1.81 times 10 to the 5th kilograms. Right? And then now I'll take the square root of that. So VF is equal to, my final velocity is going to equal 2 times 1.81472 times 10 to the 9th joules divided by 1.81 times 10 to the 5th kilograms. And this is going to come out in meters per squared, or meters per second. Okay, so let's plug in our numbers here. We're going to say, the square root of 2 times 1.81 472 times 10 to the 9th. Then we're going to say this whole thing divided by the mass of the whale, 1.81 times 10 to the 5th. Okay, and then we'll close our bracket there. Oh, we had a different bracket. Oh, that's not good. Don't mess up the bracket. You will get the wrong answer. All right, what do we get? So we get our final answer is 114.415 meters per second. And we will put that, we'll say it is 115 meters per second. That seems reasonable, but probably more like 120 meters per second. Really, it's 120 meters per second. All right, so I take, if I take my number here, 114 meters per second, and I convert that into miles per hour. So I said 1 kilometer divided by 0.62317 miles times 60 minutes per hour times 60 seconds per minute times 1,000 meters per kilometer to the -1, which is my conversion factor here, gives me 255 miles per hour. if that were true, the blue whale would be going faster than a Lamborghini. Now, how fast does a blue whale actually go underwater? I actually do not know, but I do know that our calculation here is probably wrong because, um, well, first of all, we already said that we are ignoring drag and we're ignoring the buoyant force because the buoyant force is going to be pretty significant, I would say, considering how much a blue whale actually displaces water. It's probably going to have a pretty big buoyant force, I would say. So, that is something that we are going to do today. We are going to make a correction. And so if you're watching this video, you probably already did that. But thank you for watching, and I will be uploading more videos. Now, even though this is probably much bigger, I would say, because we ignored many things, that's incredibly fast. So when a blue whale dives, if it can uh, ignore the buoyant force, which I don't really know, that would mean that the blue whale can go extremely fast underwater. Now, that's not very accurate, but this is still nonetheless very interesting. So, thank you for watching. Tune in next time and we will talk more about the physics of blue whales. Thanks for watching.
Thank you, like and subscribe down below.